Okay, we're going.
So I'm going to do time-dependent perturbation theory today, and I'm going to do it in a different way from the way that's normally done. So first of all, as usual, we have a Hamiltonian. It's H0 plus V, and as usual, I'll assume that there's no explicit time dependence in H0 or V. If there is, then there's an added complication, but it's not really significant. The time translation operator is E to minus I TH over H bar. In fact, let me just say what the difference would be. If these did have explicit time dependence in them, then this thing would be a time-ordered product. In which the earliest, well, let's see, I've got a capital T here, so I need a capital T here. In other words, this would be e to the minus I dt h of t over h bar e to the minus I dt h of 0 over h bar would look like that, and dt would be t over n, where there are n factors here. So that's how you do it if you were actually, if you had a time-dependent Hamiltonian there. I'm going to use an abbreviation. H is going to be the Hamiltonian over H bar. H0 is the free Hamiltonian over H bar. And B is the potential over H bar. This is just to get all the H bars out of the way. I'm also going to I'm going to write dt as t, which is big T over n, where n is, I'm going to again divide this thing up into a zillion, or in fact n factors of e to the minus th. So in other words, u of t, u of course stands for unitary. If the product k equals 1 to n, e to the minus I h little t. And we can rewrite that as product k equals 1 to big N, e to the minus I h0 t, e to the minus I dt. These notes are online already, and in fact I even checked them or later. Okay. Now, what you can do is you can sort of rewrite all these things, and let me well, I've actually made a slight change here, because literally this is e to the minus I h0 plus v times t. And then I'm going to say this is in the limit as n goes to infinity. In this infinite product, we can rewrite this as e to the minus h0 t, e to the minus I v t. So product of factors like that. In other words, because t is so small, you can make this change. This is similar to what's done when you do path integral formulation. In fact, this is the first step in deriving the normal path integral. But I'm not going to do path integrals today. I'm going to do something else. I'll just do the interaction picture. And now I'm going to do one more minor change. I'm going to multiply this product k equals 1 to n by one factor of e to the minus, or is e to the plus, no, e to the minus I h0t at the far end. So there's just one factor at the end, and because t is infinitesimal, this doesn't make any difference. Okay, now there's an amazing thing that happens. Namely, I'm going to take that first factor, the first three factors, e to the minus I h0t, e to the minus I vt, e to the minus I h0t, and I'm going to write it as e to the minus 2I h0t, e to the I h0t, e to the minus I vt, e to the minus I h0t. And then, when that gets multiplied by the next factor, so that the next pair, what we'll have is e to the minus h0t, e to the minus I vt, e to the minus I h0t, e to the minus I vt, e to the minus I h0t. That will look like this. It will be e to the minus I h0t, e to the minus I vt, e to the minus 2I h0t, e to the I h0t, e to the minus I vt, e to the minus I h0t. Take a look like that. Now we have one more little trick here. Namely, we write this as e to the minus 3I h0t, e to the 2I h0t, e to the minus I vt, e to the minus 2I h0t, e to the I h0t, e to the minus I vt, e to the minus I h0t. So you see there's a pattern that develops here. Each time you do this, what you get is you get three factors which represent a unitary transformation on the thing in the middle. And here another unitary transformation on the thing in the middle. And as you continue in this way, using up all of these factors, you see that you progressively get more and more terms. And eventually what you get is that this u of k, u of t I should say, becomes e to the minus I n plus 1 I h0 t, a k-ordered product, and I mean here k equals 1 to n, that's k, of e to the ki h0 t, e to the minus I vt, e to the minus I k h0 t. Okay. In other words, the k equals 1 terms here, then k equals 2, k equals 3, up to k equals big N, and then this whole factor. In other words, that's what happens when you extend this sort of shuffling out to out capital N terms. All right, so let's get, I have chocolate to reward questioners. Yes. There we go, in advance of the question.
Thank you. You've been mentioning terms, but the pi indicates a product, so maybe it's factors?
Okay. Factor would be a better word than terms. Yeah. more specific. Okay. Now, this thing that's been recurring over and over, we can define V sub I of KT as e to the I H0 KT V e to the minus I H0 KT. Or equivalently, if we put back in the H bars, the potential at time KT is e to the I H0 KT V e to the minus I H0 KT. Okay, where K is some integer, so KT is presumably finite. This is said to be the potential in the interaction picture. I think that this business of having a Schrodinger picture, a Heisenberg picture, and an interaction picture is kind of verbal overkill. And what we're dealing with here is just a simple exponential, and in the most common case where these are time independent, you don't even need to time order the thing. You've just got this exponential. You can rewrite it in this way, and when you do, well, let me go one more step. This is a unitary transformation, so we can now exponentiate the V inside, and we get e to the minus I guess I'll stay with the e to the minus I V of KT is then equal to e to the I H0 KT e to the minus I V e to the minus I H0 KT. Okay, in other words, you can go directly from there to there because it's a unitary transformation. Are we happy with this, or do you want me to see me derive this? Well, I don't have the capacity to do functional brain imaging at a distance of 6 yards. So, are we happy with this? That we go from here to there? All right. Okay, well, that means then that what we've got here is e to the minus I n plus 1. Oh, there's an extra I in this thing. That was a mistake. H0t, a k-ordered product. And now all these factors are simply e to the minus I v sub I of kt times, well, there's, yeah, let me put a t here also. Because, so I'm multiplying both sides of the equation by t, because after all we have t. Okay? So that's the formula we arrive at then. And in fact, at this point, we can also, if we think of this thing as a time, which it is, we can rename this as a time-ordered product. So it's a time-ordered product of those factors, which is the same as the k-ordered product. Now, this sum, vi of n, remember t is really shorthand for dt, which is big T over n. This plus vi of n minus 1 dt plus plus vi of dt, all that times dt is an integral vi of t dt from 0 to capital T. And these things all occur in the exponent. So in other words, the product of all that is the exponential of the sum. So in other words, we can rewrite this as e to the minus I n plus 1 h0t. And as long as we keep the time ordering, this is just e to the minus I integral 0 to big T e sub I of t dt. And now we might as well put the h bars back in. And then we get the following expression. U of t is e to the minus I h0 big T over h bar, time-ordered product of e to the minus I over h bar integral 0 to t v sub I of t dt. Okay, so that's our expression for this thing. So now, what's useful about it? Well, what's useful about it is that the original expression was an exponential. Unfortunately, I never wrote it down. The original expression, I can just write it here, was e to the minus I-t h0 plus v over h bar. And this has the h0 and the v jumbled together, and they don't commute. When they do commute, of course, the problem's trivial because they're simultaneously diagonalizable, and the eigenstates of h0, which presumably are easy to find, are also eigenstates of v. So the serious case is when they don't, and of course they never do, except in comic books. So what we've done here is we've factored out the e to the minus I h0t. Now, let me write down the more general formula. U to t2 to t1. This would be, if we had done it this way, we would have done e to the minus I h0 t2 over h bar, time ordered product, e to the minus I integral from t1 to t2, minus I over h bar, I should say, e sub I of t dt. And then down here we have e to the I h0 t1 over h bar. So in this case, we would get two factors of the h0, 1, 4, and 1 out. Okay, so the useful thing here is that we factored out the h0s. Of course, they're in here in a complicated way. The complicated way is simply that the this VI of t is E, let me get the sign right, E to the I H0t over H bar V e to the minus I H0t over H bar. So this has the free field, all right, I set it on as we'll write it, time dependent. Of H0. So that's basically, that's what that is. And it turns out that this is not that big a deal. And so, in calculations, at least in quantum field theory, people always do this. Now you might ask, did I ever do it the other way, keeping the H0 and seeing how bad it got and seeing whether this is really better? Gotta admit, no. In 40 years, I never did that. Actually, closer to 50. But anyway, so, I don't know, maybe I should have. Anyway, well, this is what you can do. Now, the application that one makes of this is essentially to the case where so this is the full time evolution operator. This then is e to the minus I t2 minus t1 full Hamiltonian over H1. Okay. Now, in scattering theory, remember what I told you that one reason why you don't want to study scattering theory too deeply is that when you change the formalism, you change the energy range of the formalism just changes completely. Almost nothing is recognizable. What one does in this context of time-dependent perturbation theory is one considers the scattering of eigenstates of H0 to other eigenstates of H0. And so that's the thing that one studies. In that case, what you're talking about is some, how shall I say, some E, maybe I should call it E0 prime, U, well, with all these other parameters, of course, it's not just a state, an eigenstate of energy, but all these other parameters, momentum and so forth. U of T2, T1, and there might be several different particles here, so, and then in here, you'll have E0 and P. We'll be taking matrix elements of this, and we'll be imagining that the scattering process takes a very long time for the beam to come in from the accelerator and to go out to the detector, and we'll be letting T2 go to plus infinity, T1 to minus infinity. These just then produce phase factors, e to the minus I, T2 minus, or I should say, T2 E0 prime minus T1 E0 time divided by H bar times E0 prime P prime, the time ordered product of e to the minus I integral from T1 to T2 of Pi of T dt E0 P. So in other words, these H0 terms, in the front and the back, of the time evolution operator just produce a phase factor out in front. As long as we're talking about eigenstates of the free Hamiltonian. The initial and final states. So our eigenstates of H0. If they're eigenstates of H0, you can toss this thing out. And so, in fact, there's something that some people define called the S operator. And the S operator, in fact, would be the time evolution operator times factors that cancel out this factor and this factor. So it would be E, instead of e to the minus I H0 T2, it would be the e to the I H0 T2 over H bar, U of T2 T1, e to the minus I H0 T1 over H bar. And that would simply be the time order product of the exponential. Right? I sometimes leave out these H bars. Integral T1, T2, B, T. So this is the S operator. And the S operator between eigenstates of the free Hamiltonian has matrix elements that differ only by a phase from the true time evolved matrix elements, time evolved by U. So they just differ by this phase. So in other words, once again, let me just call it, say, alpha prime S alpha. These are eigenstates of the free Hamiltonian. Is e to the I e alpha prime e alpha prime T2 minus E alpha T1 over H bar times alpha prime U of T2 T1 alpha. So, and then the space factor just cancels when you calculate scattering errors. In other words, only absolute value squared goes away. So that's basically the picture. All right, are there any questions? As I said, this is what I'm presenting is my own screwy view of the picture of the thing, as opposed to the standard view. Okay. Well, so no questions? All right. Well, I'm going to consider a very simple example where V is just a constant. That is to say, it doesn't itself have any time dependence at all, and in that case, Vi of t is going to be e to the I H0 t over H bar v e to the minus I H0 t over H bar. In fact, when I said that this is a special case, this is actually the normal situation, because in most cases in fundamental physics and in applied physics, V doesn't have any intrinsic time dependence, and so that is the that's what the potential is in this so-called interaction picture. By the way, this what I somehow didn't write down in my notes one of the important steps here. Let's look at this S operator, which is, as I said, time-ordered product e to the minus I over h bar integral. And I'm getting tired of writing T1 and T2. Very often, by the way, T2 is plus infinity, T1 is minus infinity. Okay, well, here's what people do, and this it's very possible that this is really something that we shouldn't do, but this is what we actually do in almost all cases. And whether this is do or not, I don't know. But let me show you the sad truth of what we actually do. What we actually do is we approximate this. What's the first? We say V is small, okay? What's the first term? Well, the biggest term, you expand the exponential, you just get 1. That's the identity operator. The next term is minus I over h bar, integral T1 to T2, Vi of T dt. Here we don't even need to bother about time ordering, because neither in the first term nor in the second is there anything that needs to be ordered, because there's only one V. And in fact, these two terms give you the leading order cross-section in all cases where they don't vanish completely. Of course, this one never vanishes, but it doesn't give you anything either. When this has a non-zero matrix element, it is almost always a dominant term. Okay, what's the next term? The next term is minus I over h bar squared over 2 factorial, which of course is just 2. Now we do have a time-ordered product. So we have a time-ordered product. Gosh, let me write this one up here. Okay, so I'm going to just, so here we go. So plus minus I over h bar squared, 1 over 2 or 2 factorial, time-ordered product. Or in fact, to write it, I think a little bit better, let's just write the two integrals. Integral T1 to T2 dt2, integral T1 to T2 dt1, time-ordered product of Vi of T2 Vi of T1. So that's the second term. And in fact, it turns out that in cases of quantum field, this term is sometimes 0, in fact often 0. This term then is the first, this term then is the first non-vanishing term. Sometimes this one, but not this one. And so there you have to time order. Now, what you're doing here, you see, is you're integrating over this whole box. If this is T1 and this is T2, and on the y-axis this is T2 and that's T1. You're integrating over the whole box, and when T2 is later than T1, you're writing this way. When T1 is later than T2, you're writing the opposite way. Okay. Well, Another way of doing that is to say you just integrate over the square in such a way that T2 is automatically bigger than T1, and that's half the square. That is to say, for any point here, and so let's see, for any point, say here, there's another point here, and here T2 would be bigger than T1. Here T1 is bigger than T2. If this is the T1 axis, I did this wrong. This would be the T1 axis. And this is the T2 axis. Okay. And so for any point here where T2 is bigger than T1, there's another point where T1 is bigger than T2. So let's just integrate over the part of the square where T2 is bigger than T1. Well, then you can just double this. And so in that case, what we have is S is equal to 1 minus I over H bar, T1 to T2, VI of T dt plus minus I over H bar squared. But we're only integrating over half the square, so we cancel the 2. Now we have an integral T1 to T2 dt2 integral from T2 to T2 dt1 Ti of T2 Vi of T1 plus higher terms. Of course, the higher terms here. Okay, so that's the S operator in this in this case. And then you can go on. The next term obviously is plus minus I over H bar cubed. And now you cancel the 3 factorial because there are 6 ways of ordering 3 points. And you can dt3, dt2, dt1, T1 to T2, T3 to... I got these backwards, didn't I?
Yeah, so the T.
Yeah, I've got right.
It's T2.
Yeah, this should be from T1 to T2. And this one should be, so this is T1, and this one is going to be T3, and this is T1. This is T1, this one is T2. VI, T3, VI, T2, VI, T1. Okay, well that's, we've got the idea here. Okay. Remember, I have questions. I've got at least 2 more chocolates, so. You have a question? All right. So this series, I think, was first written down by someone who's still alive, actually, Freeman Dyson. He's at the Institute for Advanced Study. In fact, he's been there for a very long time, and he's always been skinny. And of course, if you're skinny, you live longer. Well, if you don't get run over or shot or have some genetic disease. Anyway, he's still skinny and very active, and every couple of months he writes an article in the New York Review of Books, which is probably the best magazine, or one of the best magazines in the world, actually. And so every couple of months he writes an article. And they're always amusing to read. his specialty is having a point of view that is surprising and different. Of course, also he writes very good. Which means he writes clearly. Anyway, this is called the Dyson expansion of the Dyson series. Okay, well let's just look at the very first term of this and imagine that we start with a state I, which will be an eigenstate of H0 with an energy EI. And we look at, well, what happens to that when you hit it with this S operator? S on I. Well, it's going to be I minus I over H bar integral. And in this particular case, I'm going to change the times. I'm going to make 0 to t. And it's going to be dt prime di of t prime and this state I. So that's what happens to the state I when the S operator is applied to it. And V is some operator, constant operator. Okay. If we insert a complete set of states, and again, eigenstates of the free Hamiltonian here, we have I minus I over H bar integral 0 to t vi of t prime I dt prime close bracket. Okay, so what is this? Well, what we've got here, so this Si then, in other words, is this lead term here is just going to give us an I. And the next term is minus I over H bar, integral 0 to t, and vi of t prime I dt prime. So that's what we've got. On the other hand, this thing is easy to confuse. And vi of t prime I is just n, e to the plus I h0 t prime over h bar, v e to the minus I h0 t prime over h bar I. And these are both eigenstates of the free Hamiltonian, and so what we get is that this is equal to E, in fact I'm going to call it E to the I omega ni t prime times n v I, where omega ni is equal to En minus Ei over H bar. Okay? By the way, Dyson's most recent article is actually quite relevant to modern, contemporary high energy physics. He says, well, it's well and good that the LHC is turning on and we may learn something, but he thinks we're spending far too much money on particle accelerators and not enough on underground detection of dark matter or attempts to detect to study dark energy or do other so-called passive, in other words, experiments that don't require accelerators that cost $10 billion, or other machines that cost $10 billion, and instead work on a smaller scale. And he's done a study with just looking at Nobel Prizes in particle physics over the past 50 years or so, And he finds that 3/4 of them have come from non-accelerator experiments, and only 1/4 from the accelerator experiments. Okay, so what is our state? Well, SI now then is I minus I over H bar sum on N, and N, you can call this thing VNI. VNI is NVI. So let me get rid of this thing. VNI times an integral 0 to t of e to the I omega ni t prime to t prime. And this integral is easy to do. It gives us I minus I over H bar sum on N VNI. It's 1 over I omega ni e to the I omega ni t minus 1. So that's our expression. And there's an H bar here. When the H bar hits the omega, what we get is I, and there's also an I here that cancels this. Understand that? So what we get is plus sum on N VNI. Now I'm going to invert these two to absorb the minus sign. 1 minus e to the I omega ni t divided by En minus ei. So we've got an energy denominator of the sort that we saw in the stationary state perturbation theory. And this thing, of course, is called a Bohr frequency. You must have seen that. So this is associated with Bohr. Okay, so that's what we've got. And so what's the probability that the system is in the state N at time t? Well, it's the inner product of N S I squared, and we're assuming here that N is not the initial state itself, and so the only term that counts here is we pluck out the N here, and we get VNI, absolute value squared, the energy denominator squared, and then this structure here, which is 1 minus e to the I omega ni t, 1 minus e to the minus I omega ni t. And we can rewrite that as Pn of t is Vni squared over the energy difference squared times 2 minus 2 cosine omega t. Let me just use omega for omega ni, okay. And there's, with trigonometry, there are thousands of formulas that relate one function to another. And one of them is we can change that to 4 VNI squared over En minus Ei squared times sine squared of omega nit over 2. So this is basically a half-angle formula. And in fact, we can do one more trick by pulling back in the H bars. We can write this as VNI squared over H bar squared sine squared of omega ni t over 2 divided by omega ni over 2 squared. So we absorb the 4. Now, this okay, there are all sorts of ways of running. Yet another way of writing this is 4 dni squared over the energy difference. I don't know why I'm writing this so many times. Squared, sine squared of En minus Ei t over 2h bar. So those are all these different ways of writing it. All right, let me pause. And the first thing we want to do is we want to get out the time-energy uncertainty relation. And then we want to, if we have time, get Fermi's golden rule. Okay, so let's think about the case where omega ni, and remember that that's the difference in the energies over h bar times t over 2. Suppose that's a lot less than 1. In that case, this this thing rises as okay, so we're looking at it here. Here, when this is small, it's essentially a constant. It's a constant, but it rises as t squared, actually. But at slightly longer times, when omega ni gets around to be pi over 2 or so, then states with En minus Ei times t of the order of pi h bar start to dominate. And we get a, so let me just write this down. This is what we get is something like this. This energy uncertainty relation. But I think the better way to do it is to just graph sine squared x over x squared, which is to say Pn of t divided by h bar Vni times t. And actually, I think that's Vni. This should be squared. In any event, yeah, that should be squared. What does it look like? Well, here's a graph of it, a computer graph of it. And what you see is this is 0, so you see 1 up here. Then it falls down to about here at about -3 and 3. And then there's a little bump, and then essentially nothing. So this is 1, and what we're plotting here is this is equal to sine omega ni t over 2 divided by omega ni t over 2 squared. And as I said, this is equal to Pni t over Vni h bar t squared. Okay, so you see a certain spread in the probability. And so this is, you've got a certain spread here in energy that's allowed, and the shorter t is, the bigger the spread in omega can be. And you see, this omega ni over 2, it's basically going, to, when omega ni t over 2 is essentially pi. So what you've got is omega ni t is essentially, in absolute value, is less than or equal to 2 pi. That's where or half of that, if you want to go up to this part of the peak. And so that says that delta E t is less than or equal to something like 2 pi h bar. Or as I said, if you cut it off at the top here, then it cancels the 2. So it's pi h bar. So that's the origin then of this uncertainty relation. In other words, if there's a process that takes a time t, then, or delta t, then delta t times delta E can be as big as pi h bar, but not bigger. It can be smaller than pi h bar. And so this is said to be the time energy uncertainty. Okay. Any questions about that? I suppose I explained it in somewhat confused way, but anyway, I hope it's clear about that. All right. Well, we're not, of course, really we're talking about scattering states here, and so we're not interested in a scattering state to scattering into an individual quantum state, because that would be the precise value of the momentum and the precise angle and so forth. Instead, what you're imagining is that it's going into sort of a band of energies. And so what you want to do is you want to have the probability, the initial state going to state n, and then you're going to integrate den. So this is going to be an integral den rho of en, where this is the density of states, times this nsi absolute value squared. So that's basically what we're dealing with, and that's equal then to 4 integral sine squared of en minus ei times t over 2h bar dni absolute value squared over en minus ei squared times rho of en den. And rho, as I said, is the density of states. So rho is dnTE. So in other words, rho DE is dn. So this is basically dn. Number of final states. Now, it turns out that a delta function can be represented as a limit alpha goes to infinity, alpha over pi, sine alpha x over alpha x squared, which is the same thing as the limit of sine squared alpha x over alpha x squared, again, alpha going to infinity, or in this particular case, it's the limit as t goes to infinity of 4h bar squared over t en minus ei squared pi times sine squared of en minus ei t over 2h bar. And that is then delta of en minus ei over 2h bar. Okay, so what do we have in here? We have here this sine squared of en t over 2h bar. We also have the denominator en minus ei squared, and the rest of the stuff is just some extra h bars. So if we keep track of all of those terms, and we keep in mind that cos 1 is equal to t alpha x delta of alpha x, which is equal to alpha integral dx delta of alpha x, which is also equal to the integral of dx delta x. We see that delta of alpha x is 1 over alpha delta of x. So this expression here, another way of writing this delta function is limit t goes to infinity 1 over en minus ei squared sine squared of en minus ei t over 2h bar. So this is pi t over 2h bar delta of en minus ei. So, in other words, we just pull out, I've just pulled out these terms, and that gives us the delta function. So that means that our probability I goes to n, gen, is equal to 4 integral pi t over 2h bar delta of en minus ei Gni squared rho of En Gen. And of course the delta function, always our friend, saves us, and this becomes simply 2 pi t over h bar Vni squared rho of ei evaluated at En equals ei. Okay, so that's the probability of the transition. It's proportional to time. The transition rate, Wi goes to n, is then the derivative of this with respect to time. And that gives us 2 pi over h bar Vni squared rho of ei. So that's Fermi's golden rule. I have a story about Fermi that I'll tell you. So this is Fermi's golden rule. So let's remember what the golden rule is. This is, again, first order time-dependent perturbation theory. 2 pi over h bar, the matrix element of the potential between the initial and final state times the density of final states. That's the rate, the interaction rate, the transition rate. Okay. You remember I mentioned to you that during the early 40s, and perhaps the 30s also, certainly the 30s, he was doing experiments on nuclear physics and chain smoking or smoking a lot of cigarettes. And that eventually gave him lung cancer. And sometime, I guess it must have been 45, 46, he and Glauber were at some conference or something in either the south of France or northern Italy or Switzerland, and they were going to do some hiking in the mountains. So they went to a store to buy hiking boots. And so Glauber thought, well, here he has a chance to buy European boots, dollar strong, and Deutschmark is 0, Lira is 0, franc is 0. He'll buy a really good pair of hiking boots. Fermi buys a cheap pair of hiking boots. Glauber asks Fermi, why do you buy such a cheap pair? And Fermi said, I'm not willing enough to wear them out. I guess that was the case. This, of course, is something Glauber told me possibly 10 years ago, so I don't have it word for word. But it's a sad story. Any questions? All right, well, handy for the operator, at least.